start. So, two announcements. First of all, please, if you have to go out, try not to close the door, because otherwise people from outside won't be able to enter again. Keep track. Second, we're going to have the last group picture right after the seminar, so just go one floor above, exactly where we did it last week, and then after that we will go to lunch again. Okay. So without further ado, I think we can start with our seminar today. So it's a pleasure to have Peter Reimitz. Peter is a postdoc at the University of São Paulo, which is the other university here in the city. And today he's going to tell us about live vector mediators in forward physics and indirect detection experiments. Peter, please.
Yeah, thanks a lot for giving me the opportunity to give a talk here. And also thanks for the organizers of the school, because I mean, although I did my PhD with Tillman for 3 years, I haven't learned anything about machine learning. So his lecture right now is explaining me a little bit about machine learning, because I was mostly focused on this part of the presentation, indirect detection experiments, and how we can calculate processes to describe energy spectra in that range. So this was the first project we did, and then we used those results to just describe light vector mediator decays in general with a project with Anna, who's here today as well, and Hinata. And then we kind of took both of them together and finally have a more, let's say, complete description of indirect detection signatures in this tool together with Stefano Profumo and former students of him. So the model that I'm looking at is probably much simpler than everything we have heard the last 3 weeks. It's really just a U1 gauge group that is added to the standard model. So you really have only a gauge coupling, a new gauge coupling, a new new vector boson with a mass, and in some cases the kinetic mixing parameter, and then you have charges that are fixed. I mean, depending on your gauge group, charges to quarks and leptons.
So you don't care to X that give a mass to the gauge group?
No, I mean.
So it's decoupled.
Yeah. So I mean, there are some. I mean, I will just continue a little, and I think, there are some ways to give it a mass, but we don't really consider it in the project, yeah. So we just look at the extended sector. You have this vector field strength for the photon of the new mediator, and then some mixing that you can just add to the gauge Lagrangian. And then you, rotate it a few times, let's say this whole thing, together to shift it to couple, so this part here is then now coupled to the electromagnetic current if you shift this photon field here. And with another rotation, you get the physical photon field, and then, you can rotate to the mass basis, which is only dependent on some mechanism. For example, it's a little bit, people in our group had a paper recently where they have a mechanism to do this. So in the end, the only interaction terms, and the only thing I really focused on in the rest of in all the projects and the rest of the presentation, the only thing I would focus on is really the coupling of the C to this new hadronic current because of the gauge couplings, and this kinetic mixing if it's relevant. So if you look at those these interact, so one example as a model is the dark photon, where you just consider this part and you don't have this gauge coupling, so you just kinetically mix to the electromagnetic current of the standard model. You can have anomaly free gauge groups, where you assume that this gauge coupling is much bigger than the kinetic mixing, so you kind of neglect it in parts where you really have decays through those gauge couplings here. And you can have also so the anomaly gauge part is because you set up the charges in a way that you have, for example, B minus L, so there's anomaly cancellation between the baryonic and the leptonic parts, or other combinations of that. You can find a lot of different combinations in the literature. But you can also look at the anomalous model, so you just couple to to baryons, so it's a hydrophilic model. Again, you assume that this gauge coupling is much bigger than the kinetic mixing. Yeah, so these are kind of the models that we considered then. And if you look at how it's coupling to the hadronic current, I mean, in the dark photon case, it's just electromagnetic current. For gauge couplings, it's a new, current with the gauge couplings to the standard model fermions. But if you look at it perturbatively, it pretty much looks the same. I mean, you just go into a pair of fermions here. So the difference between those two is not that big. But if you then go to lower energies, where you had like with your mass of the new Z is around the lambda QCD, your degrees of freedoms are no longer quarks but hadrons. So you have the Z decaying into a bunch of mesons and vector mesons, pseudoscalars. So you can have final states like pi gamma, 2 pions, 3 or 4 pions, or 2 kaons, eta pi, and a lot more. So this is the thing that we focused on, like to really describe those decays robustly. And for the dark photons, so for the kinetic mixing, it's rather straightforward, because you know like those currents and how they look like from the standard model already of plus and minus annihilations. So you basically just can take this part. I mean, here you have the matrix element, and instead of, you just take this part and then couple it to the Z instead of this incoming current here. So in the end, what you do is usually you have like this ratio here, where this part of the matrix element, if it's squared and everything, cancels out. So then you just rescale the couplings in the end to get the full description of the C decaying into hadronic states. But for the gauge couplings, it's a bit more tricky, because you're not sure to which hadronic channels you really couple. So if they're mixing with the rho or omega or phi, for example, so you kind of have to break this up into little pieces and then put them together depending on which gauge couplings you have. So this is why you should look into like chiral perturbation theory, vector meson dominance, to really describe what's going on in here, in this part. So, the name of the workshop is New Direction Particle Physics, and the first part that I'm talking about is not really a new direction, because people from Darkcast already worked with dark photons, U1 gauge group extension, used chiral perturbation theory or vector meson dominance to describe beyond the standard model models. So this is rather, let's say, recent developments in particle physics. So in the first part I will describe how we improve those current calculations with really using only very little theoretical assumptions. You really build up all the subchannels on the matrix element level and consider a very large set of hadronic states, because once we know how to put them together, we can put them together to a number of final states, a large number of final states. So these three parts, we have like this the regime where you can use chiral perturbation theory, which starts at the pion mass, where you really have some mesons that play a role. But then it soon goes over to a vector meson dominance regime, where the vector mesons start to have resonance effects on those decays. And if you're about 2 GeV, you can use just perturbative results. So for the chi-pt part, you only have two final states you really can accurately describe. It's the pi gamma and the 2 pion states. In this case, you have a Lagrangian that looks like this, where the Z is coupling to pseudoscalar mesons, so you have a Z decaying to 2 pions, for example. And you add this Wess-Zumino-Witten term, which gives you a vertex like this, so this Z can decay into a neutral pion and a gamma. Then if you go up this scale to this vector meson dominance regime, you can describe all the remaining final states. I mean, for example, 3 pions, 4 pions, kk pi, and a lot more. And you can, like on the theory side, if you look at vector meson dominance, you have a few terms that play a role. The most crucial part for the rest of the talk is probably this part where you just mix the Z with a vector meson. So this gives you the resonant part here of those decays. And it really depends on how you couple how your charges of the C are. So this decides if this trace is 0 or not. For example, if you have same sign charges and you look at the row, you get a 1 and -1. So like if you have same charges, the row would give a 0 here, so you won't couple to the row meson, and everything that is connected to the row meson in the final state would disappear. And so you, for example, for same sign charges, you will still get a row part and a phi part here as a resonance contribution. Then there are additional terms, for example, vector meson pseudoscalar vertex, for example, omega rho phi. So in this case, you get another, the omega is going into a neutral pion, for example, in a row. And you have a vertex of vector meson and 2 pseudoscalars. So the row meson, for example, here is going into pi plus, pi minus. So this is, for example, a description of the 3 pion channel, where you have a resonance row contribution, then another propagator, a row propagator here to describe the 3 pion final state. So all of these vertices here give us the Lorentz structure, so we really see the momentum dependence of this hadronic current here that we collect through like all those terms. And we can parameterize this hadronic current. For example, here we have a Breit-Wigner contribution from the omega or from the row. So then we put this hadronic current together. For example, in the 2-kaon case, we have a contribution from all vector mesons. So then we have this form factor here is proportional to sum of this Breit-Wigner function, and we have the momentum dependence here coming from 2 pseudoscalars. So if we put it, if we like take all those terms from the Lagrangian, we have a set of hadronic currents that play a role in our calculations, and some of them are, for example, 2 pseudoscalars, pseudoscalar and a photon, vector and pseudoscalar, or 3 pseudoscalars. For example, this would be the 3 pion final state, this would be 2 pions or 2 kaons in the final states. And then we take those hadronic currents, the form factors, and fit it to E plus E minus data to get to fix the parameters of those of those form factors here. So for example, we have the pi gamma final state, and if we compare to DACAS, the already existing tool, we, instead of only having a contribution from the omega, we have a contribution from the omega and from the phi. Or for 2-kaon final states, we consider the neutral and the charged kaons instead of taking 2 times the charged kaons. So we get a little bit, our curve is below the one of DACAS, for example. And for kk pi, this is, we really take all these contributions separately without any further assumptions. So since we can build it up like this hadronic current, we are pretty flexible in how we do it. So we have like all those 3 currents that we can describe instead of making any assumptions about the, just considering the isospin 0 part, and then just not, for example, saying that this kk or kk pi channel have to come from a phi, but all the vector mesons can contribute to those to those currents here. So really, I mean, what we have, this is the kind of improvement that with less theoretical assumption and less simplification needed in our approach, we can really describe like the final states like separately and in a robust way, let's say. And we, like, in addition to that, we added a lot more hadronic final states, especially in the higher mass range or energy range. So this orange curve here is how close we can get to a plus and minus data. So we're really accurate until, let's say, 1.6 GeV.
So this is for assuming which mass?
Hmm?
So this plot is made for which mass?
So, I mean, so this you can change just to the mass of the C. So it would be like until 2 GeV mass in the C boson. And then you can separate these parts into a rho contribution, omega and phi. And if you remember from the beginning, it's really crucial to know if it's coupling to one of these resonance contributions here to see if, like, if depending on your gauge group, like all of them contribute, or maybe just the omega and the phi contributions here. So if we have a model with only omega and phi contributing, we expect that our results differ from the ones from Darcast because of the KK pi channels, and also because of adding a lot more hadronic states in for a little bit higher masses. And this is what we see, for example, in B minus L model or another combination of B minus L charges. We can see that we can get to, let's say, between 5 and 10% difference compared to Darcast. And we provide those results in a repository. So if you need like any vector boson decays, you can just calculate the branching ratios, the lifetime of the particle, and the hadronic widths with this tool that we provide here. So now to the new direction, you can use those results that we have, for example, to describe hadronic final state searches with phasor 2 and probably other experiments, but I will just focus on phasor 2 in this case. And you can do indirect detection with light vector mediators. So the first part of phasor, the reason why it's interesting is that so far in many models the only final state that were considered were leptonic final state. So electrons, muons, or for example neutrinos in some cases. But there's this part of the hadronic resonance region that is so far unconstrained, but a lot of experiments try to constrain this part. So we thought it's good to have a robust description of the hadronic final states in this part to really constrain it in a nice way. So the phasor 2 experiment, just to mention what it is based at the LHC in forward direction of the Atlas detector. So you expect a lot of forward-going particles that escape the Atlas detector to go in this direction of the phasor experiment, and then neutral particles from the standard model assumed to be absorbed by the LHC infrastructure, and charged particles are deflected by the Atlas detector magnets. So you really don't expect any standard model activity in those detectors, but eventually you might be able to see a long-lived particle beyond the standard model, for example the vector mediator, to decay in this phasor detector here. So we took our hadronic currents and the description and then tested, for example, the B model. As you can see in the lower mass range, the pi gamma is dominant. So you can see that in this range, the pi gamma here in pink is constraining parameter space. But then if you go to a little bit higher masses, for example, the 3 pion is constraining it a lot. And in around the phi meson resonance, the kaons can constrain the parameter space as well. So if you look at the plot that I showed before, you can really constrain like much more of the parameter space if you look at this hadronic resonance region And this is included in this Forward Physics Facility white paper. And the second part is indirect detection. So this was the original idea that we had, that we look at indirect detection and what we can do there to describe to describe just processes in general to constrain the GeV MEV range for indirect detection. And the general idea of indirect detection is that you have an astrophysical object that has some dark matter distribution here that is described here with this J factor. Then there are dark matter annihilations that produce in the end some stable particles that you then detect in your detector. So you have, like, it's kind of consists of three parts, the calculation of the number of particles arriving in the detector. It depends on the astrophysical object, it depends on the process, and it depends on, like, your telescope and how sensitive and how big it is, for example. And the part, we as that particle physics mostly focuses on is to describe those energy spectra and the annihilation cross section. So this is the particle physics part of the whole indirect detection pipeline. And the status is, this is why it's, we thought about including those processes here, is that the sensitivity of experiment here is pretty good in GeV and in the TeV scale or for really low masses, but there's the so-called Mev sensitivity gap. So there's a part of the sensitivity, especially in the Mev ranges, there's some sensitivity missing, let's say. But there are a lot of experiments that try to fill this gap. For example, the astrogram is trying to fill this. And if you look at the collaboration papers, they always show how they want to, how they are sensitive to this MEV gap. For example, this Amigo is setting sensitivity line here, or Gecko is also trying to be sensitive in the MEV range. But on the theory side, what's been done so far is you have this process, and it looks exactly like processes that you can you do at the LHC. So you have two particles colliding. They produce, for example, quarks. Then you have at the high energy scale. Then from this energy scale to a few GeV, to you have the parton shower. Then you hadronize, and those hadrons, they decay into stable particle after all. So what's been used so far is really those HEP tools, Herwig and Pythia, for example, directly, or you use tabulated values and then look at indirect detection tools or dark matter tools like DarkSUSI, Micromigas, MedDM, or the PPPC for dark matter indirect detection. But if you use those HEP tools to describe this process, you're really limited to energies above 5 GeV, and those tools don't work anymore for lower energies. So there's basically no description to describe this process. So the middle part of the indirect detection calculation for masses below 5 GeV. So what we did is we took those processes that we already calculated and extended Herwig with it in this project with Tillman and Peter Richardson. So the only thing we really have to do is to add an extra coupling here, and instead of E plus E minus, we have dark matter here now annihilating and, for example, producing the 3 pion final states and all the other final states. And then what we can make use of inside Herwig is, since those mesons have, there are decay tables of those mesons inside Herwig, so we can just use the fact, the way they decay in this Herwig tool to really in the end just get the stable particles. And yeah, so we can obtain energy spectra, for example, for the gamma spectrum or the positron spectrum. And this is where some of you have been to Tillman's lecture, and he always says that a true scientist always has to put error bars into their calculations, so he kind of forced me to do that here too. So we have these error envelopes around those spectra, and as you can see, for low masses, so when we don't have many hadronic final state and not much data. The error bars are bigger, but they get lower if you go to higher masses. And here, for example, for the gamma spectrum, we have like a peak from the pi gamma final states. And in the positron spectrum, we have like this extra bump here coming from the neutron decay if the energy is high enough. But at the same time that we implemented those things in Herwig, first we added those to dark SUSY in tabulated values as well, so you can also use them in this in the dark SUSY tool now, the tables that we can generate with Herwig. But at the same time as the Herwig, we did this with Herwig, there was a HASMA tool which is describing only decays with chiral perturbation theory. So what they did in this HASMA tool, they computed those spectra using chiral perturbation theory, and they could then also set constraints from existing gamma ray data in C and B, and set prospects for upcoming telescopes. So they really have the full pipeline from the astrophysical object, calculating those processes with chiral perturbation theory, and then even included experimental sensitivities into their program. So in this sense, it's really complete from the start to the end. The only thing missing is that they only focused on the chiral perturbation theory part. So then we started working with them together to also implement the vector meson dominance part. So we wrote a paper called HASMA meets Herwig for dark matter, where we both joined and really described it from the mass of the pion until the perturbative regime, to really have a complete tool that is needed to describe those indirect detection processes below the GeV scale. And the advantage here is, compared to Herwig, for example, that we have a full model implementation. You just set the charges and the gauge couplings maybe. Then you have compared to Herwig, it also includes radiative spectra from charged mesons. So in Herwig, the charged mesons, they don't really radiate any, it's not included that they radiate gamma rays, which is important for indirect detection. And as I already mentioned, you have this full indirect detection pipeline implemented. So if you look at spectra, for example, gamma rays, you can see that all those hadronic final states contributing in one way or the other. For example, the pi gamma gives a gamma line here, which is often what experiments search for, gamma lines. But you also get a bump here from the 3 pion final states. And then if you go to higher masses, more and more channels contribute. And this gamma peak, because it's, the cross section is getting lower for the pi gamma channel, is getting less and less. And it still depends on how sensitive the experiment is. So here we assume the resolution of like 10% of the energy resolution of this gamma peak. If it's less, the peak is of course higher. And we did this with 2 models. For example, the kinetic mixing and the B-L model. So in the B-L model, where you don't have this annihilation into and this mixing between the Z boson and this vector mesons, with the rho meson, you have less channels that contribute if you compare the upper part and the lower part here. And then you can, if once you have calculated this, you can, you can do this for every stable final state particle. So for example, positrons, we have also a line, but this time coming from E plus E minus annihilation, production of E plus E minus. And in this case, for example, for the kinetic mixing part, the 2 pion is usually dominant, or the muonic in this bump part, and for the B-L model, it's the 3 pions and this muon final states. You can also do this for neutrinos. In the B-L, where you couple 2 leptons, so 2 neutrinos, you get a gamma line here. which you don't get for the kinetic mixing because it's the electromagnetic current and the photon is not coupling to neutrinos. And what's often done in indirect detection is that they use like tables for energy spectra where you then just interpolate or maybe even extrapolate to get like the energy spectra in between those mass values. But this is difficult if you look at this low energy range, because here with every mass step you go, you like a new threshold of a hadronic final state. You reach a threshold of new hadronic final state, so the shape of the spectrum also changes a lot. For example, if you look at the positron at the 200 MeV, you really just have electrons in the final state, so you just have this gamma line, but then soon after you also have this bump here. And this can change in the shape as well, as you can see, for example, here. So it's not really recommended, let's say, to just interpolate or extrapolate those spectra, because they really change the shape and, I mean, and the size as well, if you go from one mass to the other. So in the end, since we can set also limits, we just took a few experiments that already exist and set constraints on the velocity average cross-section. So as you can see, in the case where the mediator mass is 3 times the dark matter mass, you directly annihilate into standard model without producing the mediator. So in this case you have resonance effects from the Z mixing with, for example, the rho or the phi meson, as you can see here. But if the dark matter mass is high enough to produce those Z's, for example a pair of Z's, then they decay into standard model particles. In this case you have threshold effect. So you have for example, if the mediator mass is equals the pion mass, you have the threshold of the pi gamma channel, so you get a peak here. Or if it's the eta, you get the eta gamma channel. So you have in this case it's more threshold effects that you can see, and in this case it's more resonance effects that you can see. So this is already everything. So to conclude, we provided a robust description of those hadronic decays for vector particles, and we described hadronic signatures in the phasor 2 experiment, and we can calculate limits for indirect detection experiments now. Yeah. So that's it.
Thanks, Peter. Questions?
Yeah. So basically, you also consider the vector boson as a dark matter itself.
Yeah. So you can do this too. Yeah. So what we usually did is, I mean, except in this case of setting the limits, we always plotted the things as over center of mass energy. So this could be 2 times the dark matter mass, but this could also be just the vector boson. So in this case, the vector boson would be the dark matter candidate. Yeah. So it's also possible to just consider the vector boson itself as a dark matter candidate. But in this case, I mean, it's more, I mean, really, because of it's decaying, usually then set constraints on the lifetime of the vector boson. Yeah.
More questions for Peter? It was here. So just a quick curiosity. So how flexible is your code with regard to charges? Can I put whatever charge I want?
Yeah. So in this code, in this HASMA code, you can set the charge to whatever you want. So you could only couple to up quarks if you want, or down quarks, or you can take opposite charges or equal charges, or only couple to the strange quark, for example. So there's really whatever you want. Yeah.
Something else? Okay, then let's thank Peter again. And we have the group picture. Thanks, Peter. Very nice.
Thanks.